We are moving into the second half of chapter 4, which is actually only made up of 2 sections, but we will spend a couple days on each sections because they are a little more involved. So section 4.4 is where we're at right now, and it's on something called the fundamental theorem of calculus, or I often abbreviate it FTC, and how we use that to work with definite integrals. So at the end of the first half of the chapter, we got to the point where we understood what a definite integral was. It was an integral that had boundary numbers. We called them the a and b values, or your limits of integration. And we started evaluating them using either geometry or given information so that we could find essentially a value that represented like area under a curve. So obviously there are going to be functions that are not geometric in nature that we want to know what the answer is without being reliant on a picture or extra given information. And that's where the fundamental theorem of calculus comes in. It is a theorem that allows us to evaluate a definite integral using calculus skills and algebra skills instead of geometric skills. So the theorem is actually on the page, and I'm going to explain what it means. So you are integrating from A to B. If we know that capital F is what we get when we integrate, we call it the antiderivative, then essentially what we're doing is we are integrating it and then putting our boundaries in one at a time. Notice that our top boundary goes in first and our bottom boundary goes in second, and we subtract those answers. That will give us a numeric answer for the definite integral. So the best way to explain it truly is to go through and do some. So I have like 3 or 4 or maybe 4 or 5 basic examples of this. So step 1, integrate the given integral. So using, again, right now we just mainly have power rules and basic trig. So power 1 greater divided by that power. We don't need to put a plus c here at the end. And the reason is when we put our boundary numbers in, so when we put our 1 and our 3 in and subtract, if we have a c for the first part and we have a c for the next part, when I subtract them, those c's are going to be gone. So definite integrals do not include plus c when we integrate them. The notation that you'll see is they'll put a really long bar at the end, basically indicating that the integral is done. And then you'll often see your boundary numbers at the end of that. So that's kind of the reminder of, first of all, I'm done integrating, and second of all, I do still have to work with boundaries. So then I put my top boundary in first. So I'm going to have 3 cubed over 3 minus 3 times 3. This problem has a lot of 3's. I'm going to put my bottom boundary in next. So I'm going to have 1 cubed over 3, which is just 1/3, minus 3 times 1. And I'm going to subtract. And here's where it helps to have a calculator or to work with really easy numbers. 3 cubed is 27, divided by 3 is 9, minus 9. You actually get 0 for this one. And then in here, we get 1/3 minus 3. So 1/3 minus 3 would be negative 8/3. And we end up the negatives canceling, getting positive 8/3. The answer is going to indicate area under the curve between those boundaries. Now, if you get a positive answer, what that is indicating is your area is located above the x-axis. If you get a negative, it's located below the x-axis. Here's what happens if you accidentally switch your boundaries. So we said that we put the top in first, then the bottom one, and subtract. If you accidentally do bottom minus top instead of top minus bottom, it would negate your answer, which is one of the properties we learned last week, which said if you had your boundaries switched, it negated your answer. So that's algebraically why that property works. So here's a few more that we'll kind of go through and talk through. So 3x squared, the integral of that is x cubed. Plus 2x, the integral of that is x squared. Minus 4, integral of that is minus 4x. We're done integrating. We do not need a plus c. We're going to put our boundaries in. And here's where you don't have to show as much work as I did on the last one. So if I put 4 in, I get 4 cubed, which is 64, plus 4 squared, which is 16, minus 4 times 4 is minus 16, so those will cancel. Minus, when I put 0 in, I actually get 0, which is great. I love when 0 is a boundary because it tends to be very simple, often 0. So we get an answer of 64, which means if I were to graph this function and look at what happens between 0 and 4, that is the area enclosed, and it is going to be above the x-axis because it is positive. Next one, we're going from 1 to 4 of 3 square root of x. We do have to have a continuous function to integrate, and you'll notice square root of x is good as long as we're working with 0 and above. So I could not give you this problem and put boundaries that are negative because you can't take the square root of a negative number. So I'm going to rewrite this as 3x to the 1/2 so I can do a power rule. So power 1 greater divided by that power. We end up getting 2/3 times 3, which is just 2. x to the 3 halves as my integrated answer. And then I'm going to put 1 in. So I get 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. 4 to the 3 halves, you're going to square root. You end up getting 8 times 2 is 16 minus 2 times 1 is 2, giving us 14. Again, indicating the area under the curve of that particular function. If it is trig, couple options. Sometimes it's going to be one that you're going to be a little more reliant on a calculator. Sometimes it's going to be one that actually works out really nicely. This one, I picked one that works out really nicely, so we didn't have to go to a calculator. So the integral of secant squared is tangent. Boundaries are pi over 4 and 0. So we're going to take the tangent of pi over 4 minus the tangent of 0. And these are actually things from your unit circle that you should know. Of course, you might not be super on top of these right at this moment. The tangent of pi over 4 is 1. The tangent of 0 is 0. So you get 1 minus 0, which is 0. When they don't let you use a calculator, it has to be something that not only integrates really nicely, but that your boundaries are something that you're familiar working with. And then the last one thing to notice on this one, this particular function, 1 over x squared, is not continuous at 0. So I could not give you a definite integral that included 0 as either a boundary or in between the boundaries. You'll notice that I purposely made my boundaries 1 to 4. So I went away from that discontinuity. So this is an x to the negative 2. So power 1 greater divided by that power gives me a cleaned up answer of negative 1 over x. Put your boundaries in, so you get negative 1 over 4 minus a minus, which would be plus 1 over 1, giving you an answer of 3 halves. So that is how we work with definite integrals from a very calculus and algebraic standpoint and not relying on geometry or extra given information.